that are involved in anaerobic metabolism. So before I get going on the first system, does anybody have any questions from the material that we covered on Friday? No? We're all okay with our carbs and fats and proteins idea, enzymes. Okay. All right then. Let me pull up the PowerPoint. ATP reduction, here we go. Okay, so when we're looking at anaerobic metabolism, we are looking at a time span from start to around 2.5 to 3 minutes. All right, that's the only block of time that we've got to make ATP without the use of oxygen. Okay, so there's a limited group of movements and particularly sports that we would put into that block. Okay, so we have two different systems that both produce ATP without oxygen. The first one is called the ATP-PC system. In some resources you may see it called the phosphagen system. And that's responsible for producing ATP from 0 to about 30 seconds. So a very, very short period of time, but it's typically very high intensity, or at least much higher intensity than the period before it. All right? So I think on Friday I was talking to you about the difference between sitting at your desk in the classroom and then the fire alarm going off and you getting up and walking out, right? That might not seem like a huge, really hard piece of work, but compared to sitting down, that's a big change in ATP requirement, right, in energy requirement. So we would use ATP-PC to stand up and start walking, right? And then from 30 seconds to around 2.5 minutes, 3 minutes, depending which resource you're looking at, is system number 2, which is called glycolysis. Okay? If we want to continue moving after 3 minutes without a rest, then we have to switch over to aerobic metabolism that we'll talk about in chapter 3, starting on Friday, I believe. Okay? So anaerobic metabolism occurs in the sarcolemma, in the part of the muscle cell that's very watery, where there are organelles floating around, there's inorganic phosphates floating around, and we have ATP and phosphocreatine floating around. All right, so our first system then doesn't use any of the food sources that we talked about, at least not directly, any of the food sources that we talked about on Friday, okay? And that's because from 0 to 30 seconds, you can't break down even a glucose molecule in that amount of time. Okay? So, so our food sources aren't any use to us directly during that first 30 seconds. And so what the body does is use some stored energy bonds that are just floating around in the muscle cell. Now, one of those is already ATP, all right? So we have a very, very small amount of ATP floating around in the cell that we can immediately break apart and release the energy from, like we saw on Friday. But we only have somewhere between 5 to 10 seconds, depending upon the individual and the kind of training that they do, all right, of ATP available. So we still haven't gone long enough to start getting that energy from carbohydrate, so we still need a stopgap, and the stopgap is the phosphocreatine. Okay? The phosphocreatine has an energy bond, but like we were talking about on Friday with the adenosine diphosphate, the ADP, in PC, we can't directly use that energy bond. We can steal it and rebuild ATP, and then break the ATP down and use the energy for muscle contraction. So it's a bit of a long-winded process, right? It would have been much easier if we could just break down phosphocreatine and immediately use that energy for muscle contraction. But that's not how we evolved, right? So the kinds of activities that are going to predominantly use ATP-PC are things that are very short, very high intensity, okay? So think about what we have that would fit into that little package. You know, in track and field, that's easy. 100 meters, 200 meters if you're really, really good. Any of the throwing events, long jump, triple jump, right? All of those events, and then when we look at game situations, any kind of play that is shorter than 30 seconds, are all going to predominantly use this system to make their ATP. Right? Olympic lifting, or any kind of 1RM strength test, right? Those would all be ATP-PC. So this system can only provide energy for a very short period of time. And as I say, typically it's going to provide energy either for something that's very, very high intensity, or when we're changing from something that's very low to working harder. Right, that initial bump needs some help from ATP-PC. Okay, so phosphocreatine is composed of creatine and an inorganic phosphate. So again, on the slide, I've got that chemical makeup. You don't need to know the chemical makeup. I have the picture there in case that's something, you know, if you're really into chemistry and biology, and then that might help you, right? Doesn't help me in the slightest, knowing that format, okay? So I'm going to draw the figure from page 33 on the board. I didn't like how that whiteboard with me writing using my finger on Friday, that didn't sit well with me. So I'm going to draw it here and talk you through it. If you have your textbook with you, open it up to page 33 and you want to look at figure 2.12. Okay, so we're going to look at the energy that's released from the breakdown of phosphocreatine. All right, so let's do our first 5 to 10 seconds. Okay, so this is going to look similar to what we did on Friday. We have an ATP molecule that's already floating around in the muscle cell. Okay, and we're going to break down that ATP molecule into ADP plus an inorganic phosphate plus a hydrogen plus energy. Okay. Now, what we didn't mention on Friday was that this breakdown of ATP is facilitated by a specific enzyme. And usefully in this case, the enzyme, you can't get this enzyme wrong because it is ATPase. Okay, so ATPase facilitates the breakdown of ATP and the release of energy. Doesn't cause it, remember, the enzymes don't cause the chemical reaction, they just facilitate them. Right? So this energy that's released is used for muscle contraction. Right? So that's great, but we get 5 seconds. So what do we do for the rest of the 30 seconds? All right? So for the rest of the 30 seconds, we have to rely on the available phosphocreatine that's also just kind of hanging out in the cell there. All right? So the phosphocreatine gets broken down into creatine plus an inorganic phosphate plus energy. And we have another nicely named enzyme to help us out here called creatine kinase. Kinase. That facilitates the breakdown of the phosphocreatine. Now, what we have to picture here is this energy that we've just released from the phosphocreatine cannot be used for muscle contraction, right? Only that third energy bond in ATP can be used for muscle contraction. So what do we need this energy for then, right? Well, if we've already broken up the existing ATP within the first 5 to 10 seconds, what we need to do is resynthesize, rebuild the ATP so that we can break it down again. So this chemical reaction works in both directions. Right? And the energy that we steal from the phosphocreatine doesn't go to muscle contraction, it goes to rebuilding the ATP. Okay? And as we'll see in a little while, when we start to run down our immediate phosphocreatine store, then we either have to dramatically decrease the intensity of the work that we're doing, or we have to go into a recovery phase. And we'll come back to that idea in a minute. All right? So we've got 5 to 10 seconds of ATP readily available. We've got an immediate fast resource of energy in phosphocreatine to rebuild ATP for about another 15 to 20 seconds. So this whole system can get me through 30 seconds. Questions? No? So, let's think about just an athlete for the minute, because you have to work pretty hard to get anywhere close to depleting ATP and phosphocreatine, okay? So let's just take an athlete scenario. It's very tempting when you understand this system to say, oh, well then it must be the depletion, the running out of the ATP and the phosphocreatine that makes me slow down in a 200 meters or a 400 meters, right? Or in the gym, if I'm doing some reps with a heavy weight, why is that last rep so difficult? It must be because I ran out of phosphocreatine. Right? But the research doesn't support that idea. Okay? The timelines between the depletion of ATP and the running out of phosphocreatine don't match the timelines for muscular fatigue in short, fast, or hard type events. Okay? So it's much more likely then that the fatigue that we get on that last rep that we're trying to push out, that we need our spotter for, right? That fatigue is caused by an increase in the acidity of the environment within the muscle cell. So remember, when we break down our ATP, we release some hydrogen, right? And hydrogen is acidic. So it's much more likely that free-floating hydrogen and possibly free-floating inorganic phosphates are increasing the acidity within the cell. And remember, what doesn't like an increase in acidity? What did we say on Friday? Doesn't like a change in the pH of the cell. So they don't like a change in the temperature, and they don't like a change in the acidity, in the pH. What's that? My enzymes, right? So what we think is going on here, what most of the research seems to support, is that it's the hydrogen and the inorganic phosphate that are slowing down ATPase and creatine kinase, and therefore our energy production is slowing down, and therefore we slow down. Right? If we do deplete phosphocreatine completely, then we have to have an aerobic recovery period, right? So we have to have a rest phase to give ourselves chance to rebuild the phosphocreatine and rebuild the ATP. Okay? So that's related to the work that we do in interval training. It's related to the kinds of repeated bouts that we see in sports like basketball. the recovery of ATP and phosphocreatine improves, the capacity for that recovery improves with the correct type of training, right? And, you know, if we look at the picture of how this is happening, then we can think about what would be potential areas that would increase ATP production and make me more efficient within that 30 seconds, right? So if I had more enzymes available, particularly creatine kinase, then I would be able to speed up the reactions and get more energy more quickly, right? Or if I had more substrate available, the substrate in this case is the phosphocreatine, right? So if I had more phosphocreatine available, then I would be able to make more energy within that period of time. More energy means more power, more strength, more power, faster, all good things for short, high-intensity activities, right? So if you have a look at page 34, there's a box there that talks to you about creatine supplementation, because one of the ergogenic aids that sprinters, throwers, lifters want to use, because they know that phosphocreatine is important, is creatine supplements. Okay, so they're quite popular. So there's some things to know about creatine supplementation. We don't know at this point in time whether there's any long-term negative effects on your body of creatine supplementation. There seems to me to be a disconnect in the literature over this. There's some literature that says, well, maybe over time it could damage your kidneys, or at least cause some problems. And there's other literature that says, no, we don't see any kidney problems over time. And it has to be said that right now, creatine supplementation is not a banned substance, right? By either the International Olympic Committee, nor I think by the NCAA. I'd have to check the NCAA, but I don't think so, right? So one of the reasons that the IOC bans substances is because they're dangerous, okay? So, as I said, right now it isn't a banned substance. That's because we don't have any proof that long-term use does any damage. However, using creatine as a supplement does stimulate the body to retain water. So in the short term, someone using that is going to put on up to 6-7 pounds of weight, right? Not fat, but weight, water weight, okay? Another issue that you might want to consider is that when you take it as a supplement like that, very little of the creatine from the supplement actually becomes phosphocreatine in a muscle cell. It's outside my area of research, so I don't know, but I'm assuming that somehow they tagged the creatine and then they can work out how it's, where it's ending up in the body. So not very much of it ends up really increasing your phosphocreatine levels. However, I guess if you're an Olympic 100-meter runner, you don't need very much of an edge to win the gold medal, right? So, maybe it does help enough to make that itty-bitty difference that, you know, it's hundredths of a second when you look at first, second, and third place at the Olympics in a sprint event, or a jumping event, right? Tiny little differences quite often. So given what we just discussed then, what adaptations do I see in this system if I train for high-intensity, short-duration events? Okay? The first thing to understand about adaptations in the body is that they are typically positive. All right? So an adaptation occurs when I stress a system, and the adaptation allows the body to deal with that stress and get stronger in whatever respect is necessary. All right? So adaptations are positive. So we said if we wanted the ATP-PC system to produce more ATP within our 30 seconds, we would need either a load more enzymes or a load more phosphocreatine, right? And therefore, not surprisingly, that's what we see occur, right? So one of the things I would recommend to you now is when you are studying, right, it's really important that you try not to take the route of just rote memorizing information and then spewing it out, okay? Because that's not learning, it's memory, and then when you don't use it or you finish the class and you go away, you're not going to remember it, all right? If you understand how this system works, and we understand that adaptations are typically positive, there's not a lot of learning to do on this slide because we already addressed it with what would we need to create more ATP. Does that make sense? So we do see an increase if we train the system correctly. We do see an increase in creatine kinase, in the activity of it, right? How quickly it is facilitating the breakdown of phosphocreatine. Some studies do indicate that the rebuilding of the ATP gets more efficient, a little bit quicker. And there's some disagreement in the literature about whether or not those things actually lead to an increase in performance. Right? The research is really equivocal. So there are significant increases in creatine kinase, and some studies show that in certain resistance work, so certain lifts, and in sprint cycling, we see improved performance. Other studies that have looked at sprinters or at throwers haven't seen an increase in performance, right? So it's very inconsistent right now, okay? ATP and phosphocreatine adaptations, right? Do we see more substrate within the muscle cell if we train that system properly, okay? So again, little bit of disagreement. Some studies say yes, we do see higher concentrations of ATP and phosphocreatine, right? Endurance training has no effect on system 1 because they're at opposite ends of the continuum, okay? There's some again, some question over whether having higher ATP and phosphocreatine stores within the muscle actually impacts the high-intensity performance, because the fatigue and the depletion of the stores doesn't seem to match up. Right? So we obviously have a ton of work to do in understanding how this system really works and how we can benefit athletes who predominantly use this system. Right? The ideas are there, but the research isn't showing that the idea follows through. Right? So we've got a lot more to learn about system number one. Questions? Okay, so the second anaerobic system is glycolysis, and it kicks in and takes over the role of creating ATP around 30 seconds, and it can create ATP predominantly until about 2.5 to 3 minutes. Glycolysis uses carbohydrate, right? So glycolysis is responsible for taking my carbohydrate and splitting it down chemically and releasing energy along the way, right? So glycolysis is responsible for breaking down carbohydrate anaerobically without the use of oxygen. So when you look at the diagram in the book, try not to panic, okay? Because I'm not going to make you learn the version in the book, all right? For a couple of reasons. One, if you're a biology student, you're going to have to learn it for Dr. Barlow. So you can spend your time there learning it for him. My main reason for not making you learn it, however, is that I memorized it several times in my academic schooling, and I could not reproduce that diagram if my life depended upon it, okay? So to me, it's a waste of time, right? That's why we have the internet, that's why we have textbooks. If we need to know these tiny details as coaches or PE teachers or trainers, we can go and learn them. We can go and look them up, okay? It's all the big, long words of the chemicals at each stage aren't beneficial to me as a coach. What's beneficial is, how does this work, right? How does it work? How does it impact performance? How do I train it? That's what I need to know, okay? So that's what we're going to concentrate on, all right? Now, if you remember, I'm going to draw on this diagram. Ryan, if you could make sure that it comes up on the film for me. Thank you. So, I'm going to draw an easier version here for you, okay? Remember that we said that the glucose molecule was a 6-carbon molecule and that that was going to be important later on. This is where it starts to become important. It's even more important when we get to chapter 3, okay? So at the beginning of glycolysis, I have to feed this system carbohydrate. And I have two options for that, remember. We've got glucose in the bloodstream, or we've got glycogen sitting right there in the muscle cell. Okay? So if I use glucose, right? In order to get glucose into the first molecule of the system, I have to use an ATP for that first little breakdown. Right? If I use glycogen that is sitting in the muscle tissue, it just so happens that when we break glycogen down, it turns into, the first thing it does is turn into the first molecule in the system. So I don't have to use any energy for glycogen. All right? Then we're going to go through several stages. Okay? We're going to use another ATP during those stages. And about halfway, so it takes 10 steps to break down carbohydrate. Okay? So around halfway, my 6-carbon molecule breaks into 2 3-carbon molecules. All right? And during the next half of the system, I give off, hydrogen ions that are acidic. Right? But I make some ATP. I make 2 ATP from this 3-carbon molecule, and I make 2 ATP from this 3-carbon molecule, and I end up with a molecule called pyruvic acid. You might see it written as pyruvate because it very quickly dissociates and turns into pyruvate. With me so far? Are you following?
Yeah.
Yeah? Okay.
Yeah.
So, when we look at my much simpler version, right, then I can see that if I use a glycogen molecule, I make 4 ATPs, but I use 1 ATP before the split into the 2 molecules. So glycogen gives me 3 ATPs. 1 molecule of glycogen, broken down anaerobically, gives me 3 ATPs. My 1 molecule of glucose makes 4 ATPs the same, but not only did I use an ATP before the break into 2 halves, I had to use an ATP to get it into the system. So my glucose results in 2 molecules of ATP. Okay. So now we've got this pyruvate, right? It's a 3-carbon carbohydrate-ish. carbohydrate product, I guess, right? What happens to that now? Okay? Because I've released some ATP by breaking down this glucose or glycogen. I'm not making very much glucose or glycogen though, right? So that glycolysis system is having to work a lot during my 30-second to 2.5, 3-minute period, right, to break down carbohydrate. So remember I said last week, carbohydrate's really important because if I'm an athlete and my event lasts between 30 seconds and a minute or 2 minutes or 3 minutes, then I am using carbohydrate to fuel my energy source. Nothing else. Right? So, all that protein's giving me energy? No, it isn't. Fat provides tons of energy? Yes. Not if you're an anaerobic athlete. The only substrates you can use as an anaerobic athlete are phosphocreatine, which was already in the cell, or carbohydrate. Okay. So then what happens? So my pyruvate can pick up a hydrogen, which is great because these hydrogens are acidic and they're a nuisance because they slow down every single step of this 10-step process has its own specific enzyme. Okay? So these hydrogens are a nuisance because if they build up and change the pH, all these enzymes are going to slow down and ATP production will slow down. Right? So it's very useful that pyruvate can pick up a hydrogen and turn into lactic acid, which is extremely unstable, so it doesn't last for very long, and it turns into lactate. Right? You may have heard the term blood lactate, because that lactate gets shuttled very quickly out of the muscle cell and into the bloodstream. So that's how we get rid of the kind of byproducts of carbohydrate breakdown, right? We turn the pyruvate into lactate and we shuttle that off to the bloodstream. The other thing that can happen to my pyruvate links into chapter 3. All right, so everything we've discussed so far has occurred anaerobically. It doesn't matter how much oxygen is available in the cell, right? Because I don't need oxygen to make ATP. Okay? But when I hit that 3-minute mark, now I have to start using oxygen. Okay? So anything more than 3 minutes is going to be aerobic because I'm going to have to use oxygen in the production of ATP. So, my pyruvate can become lactate, shuttle off to the bloodstream. Or my pyruvate can get just moved around in the muscle cell to a different place, and it can be carbohydrates form of fueling aerobic metabolism, which we'll come to in chapter 3. questions?
Professor, so would swimming be considered as aerobic or anaerobic?
Swimming?
Yeah.
I don't know much about swimming, which is bad because my dad's a swimming coach and my brother and sister swam for the county. If it was a sprint event, so let's say it's a 50-meter pool, I don't know what the times. Do you know what the time for a 50-meter sprint? Like free crawl sprint for a 50-meter race would be? So that's the key, right? I'm assuming it would be less than 3 minutes, so it would certainly be anaerobic. But is it ATP-PC or glycolysis? I'm not sure which one would be predominant because I don't know what the timeline is. If I'm swimming recreationally, then you're probably going to swim for more than 3 minutes at a time. As soon as you're moving for more than 3 minutes, you're going to switch to predominantly aerobic metabolism. Right? My brother, I don't think he does them now, but he had a period of time where he was doing these crazy 10-kilometer open water swims, so like out in the sea or in a great big lake, barking mad. Those things are huge because that's hours worth of swimming, right, for a 10K. So clearly aerobic. Does that help? Does that answer your question?
Yeah, it does help.
So what we're looking at is a combination of how hard am I working and how long am I working, right? And that's not to say that aerobic work can't be hard, but consider it this way, right? If I asked you to run 100 meters as fast as you could, right? And you're in pretty good shape, let's say you can do that in 10, 11 seconds, right? If I asked you to run a mile as fast as you could, so 1,600 meters, can you run that whole mile as fast as you ran your 100 meters? What do you think?
Probably not.
Probably not, right? I can't keep up that 100-meter effort for 1,600 meters, right? That doesn't mean I didn't run as fast as I could for 1,600 meters and I worked hard, but it isn't as hard as I worked for the 100 meters. Does that make sense?
Yeah.
Right? So my length of event and the intensity of that event dictate which energy system is going to be predominant. Okay? So think about this, because we haven't finished chapter 2 yet. We've got adaptations in glycolysis to look at and some other information. All right? So I want you to really think about System 1, System 2. go over them before we talk again on Wednesday. Right? If you've got questions on either of these systems, I'd like to deal with them first thing Wednesday before we move on. Because everything builds now. Right? So if there's something you're like, oh, I think I understand what she's saying, don't think, be sure. Right? If you only think you understand, then ask me to go over it again. All right? Because then we're going to chuck more information on top of this. And if this doesn't make sense, then the next piece of information won't make sense. Okay? I have office hours this afternoon in about 20 minutes. I'm going to dash home, grab a drink, make a cup of tea, sit down, get into my office hours. All right? So I'm going to say goodbye now. If you suddenly go, oh, then come see me in office hours. Okay? Or type a question into the discussion board. All right? Okay. Bye for now.